The first picture in my presenter number 3 shows a picture of the two sensors actually back to back, as if they were on the spacecraft that's actually in the lab, and you get a pretty good idea of the size of these sensors. Think of something like a large wash pail, and they actually it's not a bad analogy, because we view it as really as a bucket for collecting these particles from the edge of our solar system. Now, why do we have two sensors? If you look at the picture number 2, you'll see that these two sensors in cross-section, and they're very similar in design in that they operate in the same way, and they're fairly complex, because what we have to do is measure this very low flux of neutral atoms, and we have to eliminate all of the background, and especially light, from the signal. And the way to do that is we actually recharge exchange, or we re-ionize the particle. So the particle spends its entire time coming in from the edge of the solar system, and then in the very last little bit gets reionized and turned back into an ion. And the reason for that is that once we turn it into an ion, then we can accelerate it and move it out of the way of the light. And so the background light goes straight through the instrument when the particle is moving at a higher energy. The two sensors are very similar, and they have they have similar but not exact overlapping energy ranges. And this is really an exploratory mission. And so the idea behind having two sensors was, one, to extend the energy range, but also to have two separate measurements of the same thing. We have a pretty good idea from the theorists of the bounds of what we're going to observe, but the details are really we're going to discover when we get out there. And we wanted to have two separate measurements to really be able to say that we have measured the thing accurately, and now it's up to the theorists to tell us what we really are seeing. Now, these two sensors, the way we ionize the particles, it's somewhat exotic. And the first one on the right, which we call IBEX-High, we use a very, very thin carbon foil, so that when the neutral passes through the foil, it loses an electron and becomes a positively charged particle, and then is accelerated into the detector system. On the left-hand side, it's a little bit more exotic. We have a conversion surface in there, because the particles that the IBEX-Lo measures is a little bit lower energy, and that conversion surface is actually made out of a very, very thin layer of diamond coating onto a silicon wafer. And actually you have to convert that convert the neutrals into ions. In the final picture we show there is a picture of the actual spacecraft looking at one of the sensors, looking out to the side. So as Dave told you, on the top there are the solar panels, so the sun would be shining on the top of the spacecraft, and the sensor looks out to the right and away from the sun, away from the really brilliant light from the sun, and has a sunshade protecting the entrance of the sensor, and looks out into the heliosphere and detects these neutrals. Now I'm going to turn this over to Dr. Nathan Schradron, who's going to tell you a little bit about the really exciting science that we're going to get from these measurements.
Thanks, Steve. Well, I get to tell my favorite part of the story, which is the science of the Interstellar Boundary Explorer. It's been said a couple times, IBEX is really a mission of discovery. And what that means for us is that we really have never seen the structures that surround and protect our entire solar system. If you take a look at image 1 in presentation 4, you'll see a number of different images of these types of structures that surround and protect other stars in their stellar systems and in their parts of the interstellar medium. These, in each one of these cases, these are Hubble observations and other ground-based observatories. And what they're seeing is the very bright emissions, actually light, that's created through the collision of the outward flowing ionized material from the star and in this case, the fairly dense parts of the interstellar medium in which these stars are moving through. So because in this case, the collision between the stellar wind and the interstellar medium is fairly violent, it creates fairly bright emissions. In our own case, in the heliosphere, the emissions that are created by this interaction are dim. And they're so dim, the light is so dim, that they're not as bright as the light from our own sun and from the background stars and interstellar medium itself. So we need to invent a new technique to actually image this interaction. And it turns out that because the interaction is this major collision, it produces large fluxes of these neutral atoms, which you've already heard a bit about. That allows us to, send a probe out relatively close to Earth and be able to actually image the termination shock using these neutral atoms. So the neutral atoms actually behave as a proxy for light itself. Now the immediate question is what will we see? And you already heard from Eric that the two Voyager satellites have both crossed the termination shock. And so they crossed the first boundary of the layer that defines the emissions that we will see with IBEX. The amazing thing with both Voyager 1 and the Voyager 2 satellites is that what they discovered was completely unexpected. They did not discover the properties that we thought of in the case of the termination shock. And what that means for us on IBEX is that we know very little about what we're going to see. We kind of know the limits of what this interaction might look like. If you take a look at image 2, you can see model ENA fluxes. And there's actually two different sort of egg-shaped diagrams. These are both full sky, all-sky views of what the termination shock might look like in different limits of the interaction. There's a strong limit and a weak limit, and I won't go into how those things are actually defined. But you can see just how different the two limits of this interaction could be. In fact, these images are completely dissimilar. So at this point, we are headed into, we have a mystery on our hands as to what the heliosphere will look like. And 6 months after we start taking data on the Interstellar Boundary Explorer mission, we will have our first all-sky image, and we will start to actually resolve what our heliosphere, these protective boundaries around our solar system, actually look like. So that brings me to the last point. Why do we care about this? Why do we care about these protective boundaries? Well, what we've already heard is that these boundaries separate the outflowing solar wind from the interstellar medium. And it turns out that the interstellar medium, which is part of the galaxy as a whole, is actually a fairly harsh environment. There's a very high-energy galactic cosmic ray radiation, which is dangerous. It's dangerous to living things. If you're traveling out as an astronaut, you worry about these galactic cosmic rays. And you worry about the doses that they would generate. So if you take a look at the image 3, there's both an image and an animation that shows what happens when this galactic cosmic ray radiation hits the outer boundaries of our solar system, the heliosheath and heliopause. And what you find out is that about 90% of that galactic cosmic radiation is actually shielded or deflected away from our heliosphere. So these boundaries really protect us from the fairly harsh galactic environment. The other reason that we care about this mission is because it's really a part of our outward journey of robotic exploration. We have, through the space age, explored the region around our own Earth, discovered our magnetosphere and the protective boundaries surrounding our Earth. We've also discovered the solar wind, the properties of the planets, and these protective boundaries surrounding the planets as we go where Earth is with respect to the Sun and the solar system. And now, with IBEX, we're about to discover our own place in the galaxy.